Hello everyone. Today we will talk about what spinors are. Now to talk about spinors, we must first talk about the infamous Stern-Gerlach experiment. Here is a brief rundown of what the experiment demonstrates. So the whole basic premise is that you have some magnet and you have some charged particle. And you just shoot the charged particle through the magnet. Now, it turns out from experiments that if the charged particle is spinning, then the charged particle will either go up or down once it enters the magnet. And if the charged particle is not spinning, then it just goes straight through the magnet. Pretty simple, right? Now, what happens when we repeat this experiment with electrons? Well, we have a magnet that's shaped weirdly for some reason. Now, when we shoot electrons through the magnet, they would either go up or down, like the spinning charged particle. Now, obviously, electrons are charged, right? But does this mean that they're spinning? Well, if we do calculations, it turns out that it's impossible for electrons to spin since they're moving too fast. For them to maintain a spin, like a physical spin, they would need to move faster than light. So electrons can clearly not be able to spin. So if they can't spin, then why are they being deflected up or down when they meet the magnet? Well, it turns out that we don't really know. There's no actual answer that we know. And this might seem counterintuitive. Like, you could Google explanations of this Stern-Gerlach experiment, and you'd find like all these answers and stuff. But in reality, none of these answers truly describe like why it's going through. They only describe like how it goes through. And I'll get into that in a second. So yeah, basically we don't know why the electron goes like deflects after it goes through. Like, we think that it should go in a straight line, but that's not what matches experience. And the electrons cannot spin. So something else must be going on here that we just don't know. Now, we call electrons that go after electrons go through the detector, if they go up, we call those electrons spin up electrons. So if the electron goes up, we call it spin up. And if it goes down, we call it spin down. So that's just a label for electrons that go up or down. If it goes up, we just call it spin up. If it goes down, we just call them spin down electrons. It's just a label for organization. And we can actually write a symbol for spin up as a shorthand. As a shorthand for it, we are going to use this symbol over here. And for spin down, we are going to use this symbol right here. So, spin up and spin down are just labels for electrons that go up or down. That's really all there is conceptually to spin. That's all what it means. And it's pretty clear, right? It's just a label for whether the particle goes up or if it goes down. Now, some people will try to say that the electron having spin up caused it to go up, or having or it being spin down caused it to go down. But that's technically using circular logic, right? Since spin up is just the label for it going up, and spin down is just a loop for it to go and spin down. It's just a loop for it actually going down. We can't say that caused it to go up or down, since they're just labels for the results of going up or down. So yeah, we don't really know why like electron goes up or down, but we can still categorize it going up or down by using spin states. And here is an analogy if that did not make clear sense. So let's say that there is a girl named Sally. And Sally loves to eat chocolate. Sally loves to eat cookies. So she has her cookie jar over here, filled up with her favorite kinds of cookies. So Sally has two favorite kinds of cookies. She likes chocolate chip cookies, and she also loves to eat marshmallow cookies. And her cookie jar are filled with just chocolate chip and marshmallow cookies. So, Sally would reach into her jar, and she'd just take one cookie out. It's either going to be chocolate chip or marshmallow. Now, Sally actually picks her cookies like randomly. Like she just like puts her hand in and just grabs one out without looking. And if Sally grabs a chocolate chip cookie from the jar, we say that Sally is in the chocolate chip state, as a shorthand for her grabbing that chocolate chip cookie. And if Sally grabs a marshmallow cookie from the jar, we say that she is in the marshmallow state. So again, there are some cookies in the jar. She pulls out a chocolate chip cookie. We see that she is in the chocolate chip state. She pulls out a marshmallow cookie. She is in the marshmallow state. Now, does this mean that her being in the chocolate chip state caused her to pull out a chocolate chip cookie? Well, no, that's not true. Since her chocolate chip state is just a shorthand for her pulling that cookie out. We don't know what actually caused her to pull it out. Again, she just chose them at random. Like, the underlying mechanics of why she chose the cookie are unknown to us. We don't know them. Maybe there's like some force out there that caused her to actually choose that chocolate chip cookie. But as far as we know, it's random. So we don't really know why, like what causes her to even choose the cookie in the first place. I guess that's a better analogy. But yeah, she either chooses chocolate chip or marshmallow. And if she chooses chocolate chip, she's in that state. She chooses marshmallow, she's in the marshmallow state. This is a direct analogy to spin. If the electron goes up, it's in the spin up state. If it goes down, it's in the spin down state. The spin up state and the spin down states are just labels we use to describe if it goes spin up. If it goes in the up direction or down. Why does it go up and down? We don't know. Like, why does Sally even choose cookies? We don't know, but we know that she just does do that. So we can actually describe spin states in a more mathematical way. Say prior to Sally choosing cookies, there is some probability that she chooses chocolate or marshmallow. There's just some probability beforehand. Like, there may be a 50-50 chance of her choosing chocolate or marshmallow. There may be a 20-80 chance for choosing chocolate and marshmallow respectively. It's just a probability of her choosing chocolate chip or marshmallow. And same with electrons. Before the electron goes through the detector, there is a probability that it's going to like go up or go down. In other words, there's a chance that it's going to be spin up or spin down. Now, how can we model that? Well, there's one way to do this. We can say that the electron beforehand is not in spin state up nor spin state down, but in spin state psi. Now, what is the spin state psi? Well, spin state psi is a superposition of spin up and spin down, which is just a linear combination of that, where alpha and beta are complex numbers. So what does this mean? Well, we write the spin states before it goes through the detector as some combination of spin up and spin down. And so why do we do this? Well, because a squared gives us the probability of the electron being in the up state once it goes through the detector, and beta squared gives us the probability that the electron goes to the down state when it hits the magnetic detector. So yeah, just like we said earlier, there are some probabilities, and we write these probabilities as the squared value of some coefficient. These coefficients, we stick them right next to these vectors over here. So yeah, so we write the spin state as some combination, and from the coefficients we can get the probabilities. So from the probabilities, we just get that's how we can model the spin beforehand, if that makes sense. Sorry if that's not clear, but I hope it is. So let's just recap. The electron can be in spin up or spin down when it hits the detector. Beforehand, the electron has some combination of spin up and spin down, where these coefficients are complex, which means that they can be written as some real part and some additive with some imaginary part. So, a squared gives you the probability of it being in the up state, beta squared the chance of being in the down state. Okay. And we call this general spin state, and another word for that is spinor. A spinor is just the general spin state. It's just another word of saying superposition of up and down. That's what a spinor is. So yeah, that's pretty much all there is conceptually to spinners and spin states. But there are some more mathematical properties that they have, and we are going to explore some of them right now. So it turns out that these spin states, up and down, if we they're like actual vectors in a mathematical space, they're vectors. So we can take the dot products of them. Now think this is just a definition of it, but the dot product between spin up and spin down is 0. And the dot product between spin up and spin up equals the dot product of spin down and spin down, which equals 1. So in other words, spin up and spin down are orthonormal to each other, since they have a length of 1 and they are at 90 and they are situated at 90 degrees from each other. We can write these spin states in a more abstract way and say that En dotted with Em equals the Crochet delta and M, where the Crochet delta is 1 if N equals M and 0 if N is not equal to M. Now, E1 is defined as the spin up state, and E2 is defined as the spin down state. That's just an abstract way of representing the spin up and spin down states. Okay, so what's next? Okay, so yeah, remember how square value of alpha. This is the probability of it being in the up state. And for beta, down state, well, it makes logical sense that alpha squared plus beta squared should equal 1, right? Since the probability should always add up to 1. There should be 100% chance that it's either in the spin up state or the spin down state. So, in other words, the sum of alpha squared and beta squared must be normalized. They must equal 1. It turns out that from this, the dot product of the spinner with itself must also be 1 from this relation. We're going to prove that right now. So, a spinner is just some combination of spin up and spin down, or again, alpha and beta, or complex numbers to nature. We can write this in the abstract Einstein notation, where C1 is defined as alpha, C2 is defined as beta, and E1 is defined as spin up, and E2 is defined as spin down. So we can multiply. You can multiply the spinner by itself, which just equals Cn, Cm, En, Em. Now this just equals the current delta, and M, which is just 1 if M equals N. So you have the spinner dotted with itself equals Cn, dotted with Cn star. There should actually be a star here, which just equals Cn squared. And so since Cn squared must always be 1, then the dot product of the spinner with itself must always be 1. So spinners are unit vectors. They must always be normalized. So we can actually draw spinners in mathematical space. We just have some coordinate system over here. You have 0, you have 1, you have 2, 1, 2. And the spin up state will look like this. The spin down state will look like this. And the spinner state should be some superposition of spin up and spin down. Which will have a length of 1, by the way. So yeah, that's just one way to draw spinners. Well, I think that's the only true way to represent, not really a representation, spinners are vectors, spin states are vectors, that's just how you draw them in the mathematical coordinate system. So yeah, that's pretty much. Oh, one more thing. We can actually prove given this a spinner and a spin state, we can actually find the components. So let's do that. So a spinner is a combination of spin up and spin down. Again, we can write that in the abstract form. You can multiply both sides by EM. So you get EM, delta and M. Here's the N, M sin N. Have En times the spinner equals Cn. Which means that alpha equals spin up times the spinner. Beta equals spin down times the spinner. So yeah, so we can solve for the coefficients with the spinner and the spin state. Okay, so if the spinner is spin up, then alpha equals 1, right? Since they are unit vectors now. And if the spinner state is down, then beta is 1. And this makes a lot of logical sense, right? Since alpha squared gives you the probability of getting the spin up state, and alpha squared is going to be 1, which means that the spinner state is guaranteed to remain in the up state. say if our spinner state is up, then this would be 0. So the probability of getting the spin down state would be 0. Probability of getting the up state will be 1. And this makes logical sense, right? Since the spinner, it's just alpha 1 plus alpha up state plus beta down state. So if alpha is 1 and beta is 0, if the spinner state is just the up state, that means the up state equals alpha up plus beta down, which means that alpha must be 1 and beta must be 0, which means that it must be in the up state when measured. So that's like one exception. Like we usually before it goes through the detector, it's not in the spin up state, nor is it in the spin down state. It's in some combination of that, which is true. But the combination can have alpha 1, beta 0, and vice versa. So like when the electron goes up, it could have always have been in the spin up state. The spin up state just means that it's going to go up when measured. So when you measure going up, of course it like went up. It's 100% chance that it went up since it just went up, right? So yeah, that's like the whole spin state thing. There are some other cool like mathematical properties of spinners. There is Clifford algebra representation of spinners. There are like the space-time algebra. Well, those are for gamma matrices, but there's like the Dirac spinner solutions to the Dirac equation, like their spinners. There's a block sphere. There is some like cool, like there's like extra cool things about spinners that we are going to like dive into in later videos. Yeah, like in this video, just give like a brief intro to spinners, and there's like some more cool things about them. They're like really interesting properties. Sorry, they're really interesting objects of study. So yeah, see you guys in the next video. Have a great